This the full schedule?
Yeah, this is
Yep.
the latest schedule. We're probably going to have to run into Tuesday, November 4th. Class is at 8:30 tomorrow, right? And Rachel, Nina, Bradley, and Isabel are up, right? Who's going to start at 8:30? Anyone want to make a commitment?
I'll do it.
Okay, so you'll be here. You don't have to videotape tomorrow, right? Anyway, there are a few extra copies of the schedule. Jerry will send it out. I'll put it down. Unfortunately, we need, on November 3rd, we need one student to switch to another date because that's the people who transferred from October 17th, which is this Friday when I won't be here. Oh, here, so you can sign up for it. There's a few extra copies so far as that goes. Okay, sorry.
Hey, it's perfect timing.
Okay, thanks.
All right, good morning, guys. It's the last lecture. After that, we turn it over to you. I hope you had a good holiday yesterday. I want to wrap up a little bit the corrosion. I was going a little fast in the end last week about the stainless steel. I think we went through the details of the copper. So copper is on the left-hand side, where I was essentially saying if you lose the passive layer, and I've improved a little bit the image here so you can see better. There's a circle around the hole, and that's where you had essentially a deposit. So there was this crevice effect where the local conditions were different than the general pipe condition on the inside. And that created a cell to completely consume the copper locally all the way through the wall. And then you had a little leak, and the leak sealed itself because all the minerals of essentially vaporization of the water coming out of the hole. So the stainless steel example I had is brushed stainless steel. It became very popular probably the past 10 years or so, as opposed to kind of a dull finish. What happens is you scratch it enough that you don't see the scratches anymore on the stainless, so it gives a more regular appearance. It doesn't show the wear, and you can see the brushing. It's horizontal on these little. There's a little texture as well to this. So the brushing was done definitely with a stainless steel tool, so you don't have that contamination that we talked about. And the problem was, it's a rough surface, and the rougher the surface, I don't know if you've seen, you can get polished aluminum wheels for your car or truck. One of the reasons for going polished is it's more resistant to corrosion with the chlorides in the winter. It's not immune, so even with polished aluminum components for cars, if it's not clean enough, if you have enough chloride for enough time, you can start pitting through it, because it's essentially unstabilized the productive layer. In the stainless steel, it's the same situation. So I get some chlorides. It could just be moisture. This was Miami Airport, and they had all these nice structure. It was intended for kind of aesthetic purposes, just to hide structural components. And over time, there's enough chlorides to locally unstabilize the protective film, and that's where you get these little holes here. And what the part that I mentioned in more details is, even if you clean those holes, because you created that high roughness, it's easy to recreate the cell and start corroding again, and that's what happened here. So this was clean and actually sanded, so you don't even see the brush pattern anymore. Over here it's sanded, so it's kind of a dull finish, but it was too late because you had all these little holes, and it's hard to get all the contaminants out of the holes as well. So anyway, by the time that you have created the geometry, created the pits, the only viable option that I proposed was essentially to coat the surface. It's not a coating that was meant to be moisture resistance. It was actually the opposite. It was just a very basic transparent coating to prevent the chlorides from going to the surface. So you're okay with moisture. And that's what I mentioned about the difference between protecting stainless steel with a transparent coating and protecting steel. If you try to protect steel and you get moisture, then you start getting rust on the interface, and that's the problem because the moisture goes through the film very easily. But the chlorides don't. So it's easier to protect stainless steel against corrosion, although the coatings are not necessarily as resistant. So you need to do it periodically if you want to maintain. Like it's a problem for naval applications. So if you have a boat, it looks great, but you have to keep maintaining it. Otherwise, you'll start getting some local corrosion. Same with the copper on fancy vessels like private boats. This is another slide that I went through a little too quickly with the stainless steel. So you have the temperature on the vertical axis, and then you have the chloride level. Seawater will get you in the 10 to the 3, I believe, 10 to the 3, 10 to the 4. There's a lot of salt in water. So if you have stainless steel in water, it's likely to start pitting. If it's just a standard grade, which was the 316 we discussed, or lower grade. So in the stainless steel family, 316 is normally considered a good grade. It has nickel and molybdenum that they both help to stabilize the passive film when you have chlorides. So 304 is kind of your basic stainless steel for general use. 316 is better. When you put the L, it means low carbon, and that helps for welding. So anytime we do welding of 316 grade, we use the low carbon because the carbon are going to combine with chrome otherwise and reduce your protection against corrosion. One alloy that a lot of times you don't want to see is 410, and I'll just cross it up if you're thinking about corrosion protection. It only has chrome. It has the very minimal protection. So anything that happens with the environment, all of a sudden you start corroding this type of alloy. It's only used for the reason it's much less expensive than the other grades of stainless steel. One way to identify it is these are non-magnetic. Generally, if you deform them, you can start getting them magnetic. It's austenitic stainless steel, so it has this FCC structure, and that's non-magnetic. This guy is, so it's an easy way. I actually do that all the time. If I'm going to check a stainless steel, I bring a magnet to see if I'm looking at something that's I consider, corrosion resistant. The other alloys here are used as well. The 2205 essentially has a lot more alloying element. I would say each step I'm not sure the step from here to here, but from here to here you can double the price, and here to here you at least double it again. And you can keep going. Yes?
Looks like there's like 2 lines for each alloy.
Yes, and I didn't put that in. One is for the crevice corrosion, the other one is generalized corrosion. So if you have one area that's protected, yet you have a deposit and another surface, it's going to start earlier because it's that cell formation. So if it's kept clean with the 316 stainless steel, we're talking about 1,000 ppm. If it's really dirty and there's one area that is essentially sheltered from the oxygen, it's going to be less stable in that region because you rely on the oxygen for the protective film, and then you can start the pitting more easily. Which one? Oh, well, so the temperature here is really, it's a thermodynamic condition. So the higher the temperature, the easier it is to start a process of pitting. You have more diffusion, essentially. More fluctuation. It's the same as our nucleation discussion. All right, so we'll talk about some special processes. I've been wanting to talk to you guys a little bit about thermal spray for 2 or 3 lectures. You've probably seen it at the last bit, so we're going to do that now. And then I'll talk about a few other processes that I think you'd be interesting. The general idea to take a powder, essentially, or a wire, and either generally through melting, although you can do it in the solid form as well, the idea here with thermal spray processes is you project it on the surface and you can either put a coating or build up from scratch. It's more common with thermal spray to just add a coating, and one of the reasons is the same as with welding. You get a lot of residual stresses here. So if I come each time and I take a powder, so the thermal spray process, the bottom line is you have a powder or wire. You heat it up always, and then you send it to the surface at relatively high speed depending on the conditions. So say this is my substrate. And typically it's going to form these little splats, they call it, and you can build them up one after the other. So the particle hits the surface and essentially either mechanically deform and adhere to the surface. That's the cold spray here. Or you do it at higher temperature. You can do it in a fuel environment, so it's just thermal heating the powder, or you can use an arc to burn that wire. So you're very close to a welding condition, except that you run a gas at good velocity to project on the surface. It's used for ceramics, for metals, and you can do all sorts of composites of the two. You can do tungsten carbide if you want. The problem, as you can see here, as I'm building up this layer, I'm keep adding residual stresses. So I'm only going to be able to do, say, 1 millimeter or so before I start debonding that interface, because I keep adding and adding residual stresses. So the only option, I could go and heat it up and do a relief of residual stresses and then continue, but then all of a sudden it becomes more expensive. Yes?
Is this the same as spray pyrolysis?
No, I don't think so. The thermal spray processes, I don't think I have a time history here. It's really been starting just with flame or electro arc melting, and then over the years, so this is all the 20th century essentially. They kept adding new and new variations of it, and you have a lot of names, but thermal spray is kind of the general term. It's used to coat these blades, so I also carried those around a little bit, and the idea here is on a turbine engine you have a pretty hot environment, and you're always going to want to increase that temperature because that's how you gain efficiency, by being hotter. And you need materials that have a good toughness, and that's why you essentially look at super alloy and metals essentially that have ductility. Now, most of the times you also need oxidation resistance. It's so high temperature that processes like thermal spray is what you use. You create these little particles that are melted. If we're thinking about putting a ceramic, and then we hit the surface, it just flattens, and you get both a certain amount of fusion. So sometimes you will melt the previous layer, sometimes you don't, and that defines the boundary about whether you have a mechanical attachment or whether you have a solid layer. It's used for putting zinc also on steel, because we talked last time about using, and I can circulate these around, they are hollow because you circulate a gas in it for cooling. And a lot of times they also poke little holes through the whole wall of the blade to get some air to go from the inside out and create a little boundary layer. So metal, then a ceramic, most of the time is in between. You have a bond layer that will allow for the difference in thermal expansion. And then you have a little air boundary layer, and that's how you can get not exactly at the melting point of the metal, but you get close to the melting point of the metal in terms of the air temperature, the combustion gas temperature. So it's very optimized, and it's kind of a specialized field. It's an example of structure here, a ceramic, and you can see some very, very tiny cracks between the different splats. Now, we could think of these as being a problem, although because the ceramic has such a lower thermal expansion coefficient than the bulk alloy, having some cracks can actually increase your apparent thermal expansion coefficient. So it is used in practice, and there are other ways, of course, to put the ceramics on the blades. One is chemical vapor deposition, and in that process, they also make use of a very columnar structure, columnar grains that will break apart, and during service they actually will open and close a little bit, and that's how you account for your differential thermal expansion. It's unfortunate because essentially everything that resists higher temperature expands less, and that's what is exposed to the highest temperature here. We have sometimes the opposite. So we talk about essentially the ceramic here. They have alumina, but zirconia is more common for this application. But anyway, so if I have the alumina and I have the nickel layer, and then say I have a superalloy. And this, when we say superalloy, a lot of times it just means a little bit like the aluminum. You have a lot of precipitate, you have a lot of second phases into your base structure. So it's almost a metal matrix composite. So you can get as much as 50% volume dispersion into a superalloy. So it's kind of a two-phase structure, and the dislocation can go through from one to the other because of that coherence. The very same way you straighten aluminum alloy is how you make a good superalloy, essentially. So from here to here, your temperature keeps going up. This is wanting to expand less. So it actually helps us here. It does help us. So if I have less thermal expansion and a greater temperature, that's how, and here it's exposed to a lower temperature and it's expanding more, I'm kind of evening out a little bit in terms of getting the same strain at all the locations. So it does help us. A lot of times there'll be a little bit of a toughening. Yes?
But doesn't that add residual stresses inside the material?
You'll always have residual stresses in this layer as you build it. When you expose it to the temperature, the first exposure, a lot of times it will have a good amount of relaxation if it's high enough. So you have a little bit of creep and a little bit of movement. You can have little micro cracks that are forming that were not formed yet. And then you get a more steady behavior. It's one interesting, I actually worked to study the thermal expansion of these types of structures, and the first heating and cooling cycle was always a very different behavior than after the fact. Very good question. Yes?
It doesn't seem to be like a very oxidation resistant layer though, right? You're not really sealing substrate.
That's right, and part of and that's why the bond layer, depending on how it's made, a lot of times is the ultimate barrier against oxidation. So if I have a little columnar structure that's made by chemical vapor deposition, there will be some gas penetrating all the way to the interface, and that's where you need the protection. Absolutely, good point. So I emphasize a little bit the turbine blade examples, but it's an old word for this process is also metallization, and that's where you put, say, a hard alloy, say a cemented tungsten carbide. So it's a combined powder, and you project it to the surface, so you can compensate for wear. It's used on drill pipes. They'll come and they have the drill pipe, and then they're going to add metal through thermal spray all around it, and sometimes they'll machine it, make sure it's all set, and then it goes for service again instead of replacing the whole pipe. The pipe tends to wear over the tool joints where it's a bigger diameter, so they only need to do it there, and they'll do it regularly. There's no limit on how many times you do it there. A few other processes. So we were talking about a potter, and there are many ways, industrial methods to make very fine potters. I can't get to the details, but you can make it very spherical by atomization typically, or you can go through a certain heat treatment method that will make it more flaky. We put in cereals, if you look at cereals, you have iron added to cereals for health, and most of the times they come from the same process that we also use to make parts. It's who came first, I'm not exactly sure, but essentially it can be very cost efficient when it's all industrialized, and say you make the potter and it's not exactly homogeneous, then you can have screens so you can sort it by size, so your process has some variability, and then you screen the different size potter and then you sell them for different applications essentially, and you can make a bunch of different alloys. Most of the times we're talking about a relatively large volume fabrication. If I say I want this type of potter, well, nobody's going to say, okay, yeah, I'll make I'll make a few pounds for you. It's typically very large quantities. So if you're looking to make a very, very specific alloy, sometime you may have to mix different potter, and then you get this heterogeneous structure that you can heat hot enough to get the alloy that you're looking for. It looks like a very complex way to do it, but I've seen tungsten parts for high temperature application in X-ray machines and other systems where they will do it that way. They'll mix different potters in the proportion they want. Then they go through this process here of, so this is what you have. You take your potters, you put lubricant, you compact, and then you go through the sintering process. Sintering is high enough temperature to get diffusion. So if I started, let's get this here. If I started and say I got my particles this way, so I created by mechanical deformation a good amount of interfaces. By diffusion, I can essentially continue moving my interface this way, and in sintering, the volume of the part is always going down. It is moving enough to start feeling these voids by surface tension. A lot of times you will need a special environment to make sure you don't have oxidation at that point. It's very hard to get 100% density through potter metallurgy. Thank you, Jerry. But it's useful process. Sometimes it is, again, combined with machining. They call it mold-free or machining-free. So you can make sometimes parts that you'll actually use just like that. You don't go through any post-processing. Although if you're looking at sophisticated gears, it's used for gears for the main reason that you can make complex parts. And gears are often made in large quantities. Because if you're going to go through this whole process and figuring out exactly how much shrinkage you're going to get, what the geometry of mold you need, make those molds, there's a lot of process development involved. It's not as expensive as forging to develop, but it is fairly expensive to determine exactly how you're going to do it. And then you want to make multiple parts of it. Yes?
How does the strength of one of these parts compare to if you had an actual machine version of that material?
It's a very good question. So the strength for just one pull test can be pretty good. What becomes more the difficulty is if you have cyclic loading. In cyclic loading, your largest defect in the microstructure is going to be where the crack starts. And you didn't really get the opportunity to use deformation and just close these voids, use diffusion to heal everything. So if there's a contaminant, you have a particle that is not the alloy, it's a little bit of an oxide that came into your incoming powder, which is not unusual, then you start with a micro crack essentially at that location. So we don't use these parts intentionally for fatigue resistance. You could still use it. It's used in gear, like I mentioned, but it's not really the best way to get the ductility. Yes?
Are the grain sizes, those are going to be determined by?
Your powder and the sintering. So there's this cool idea to make kind of nano-grain powder to try to make nano-grain parts, but the problem is you're going to heat it up along the way. You can do it, what we call cold spray is kind of warm spray. So you just heat up the powder hot enough that you create it's soft enough it will deform and interlock with the previous layer on the substrate, but it's not as strong. And that's a way that you can maintain your original grain structure. Otherwise, typically, when you do the sintering, you move all those grains, and then the grain become still fine generally, but more determined by your sintering process. And a good advantage for wear resistance is when I mix two different powders, I get a two-phase alloy that is more stable to prevent grain growth when I go through these high-temperature sintering process. So that's why we don't go through deformation processing here to refine our grains, if you remember what we were talking about earlier in the class. Yes?
What's the purpose of impregnating it with oil?
That's if you're going to go to joining here. Machining, these are optional methods. One advantage, if you're going to go through this, is if you worry about corrosion, then you seal your part so it doesn't corrode internally. Because that would be the worst. You make a nice steel gear and then it starts corroding all the way through it very quickly. It's not 2 mil per year on the surface, it's everywhere, right?
So is that just corrosion protection then?
Yeah, to prevent the environment from coming in and creating any effect. It's used for gear. Another way is if you know it's going to be lubricated, you can think that you're essentially going to end up with lubricant inside your alloy when your pores are not fully closed. If it's sintered enough, you can get, again, these parts that essentially will be penetration free. But in a typical process, you end up with some residual pores that are interconnected. Yes? This is what I'm using right now for building up a prototype. Let's see. Direct metal laser sintering. There are a lot of different words for it. It has limitations. Okay, it's just like 3D printing. We say, okay, you can 3D print anything out of plastic, but the main limitation, as I got to learn both for plastic and metals here, is of course you can direct the laser anywhere you want. The problem is you're going to melt the alloy, and that alloy is going to need some support. Is a typical issue. So if you try to make this shape that goes from a smaller diameter to the bigger diameter, you have to worry about, is the powder is going to be strong enough to prevent the whole structure from sagging, because it's going to be really hot here. And therefore, there are limitations in how you can grow in size or reduce in size. There are also limitations on minimum feature size for the same reason. It's not a question of focusing the laser, it's a question of what happens once you melt. Yes?
So with this, do you just have a lot of powder and then wherever the laser hits is where?
It's going to melt, and then it cools back and form the shape. And then you come again and you form another layer. I have an image of it here. Let's skip to that, where you can see the individual melt pool, just like welding. And these are, for that example of a nickel-based superalloy, this is a student that was doing a project for a company. you can see you melted at least 100 or so of these little particles on each melted pool. So if I use a smaller potter in this case, it's not going to make much difference. What I would want to do is reduce my melted pool size if I want to make more intricate geometries. So just going quickly, it's exactly like you guys said. So you bring in some powder and then you keep it flushed here and you focus the laser. It doesn't have to hit directly. A lot of times there are condensing systems, and you scan and you melt point by point what you're interested in. Then you keep lowering this, you bring more powder, and you keep going and going and going until you're done. You do want to have a way. You can't really make a closed object unless you're willing to say it's going to be full of powder in the end. So you need a way to get the powder out of the way, and a lot of times you need more support than what's advertised. And this schematic, I don't know, most processes won't do that turn here. That's almost 45 degrees without building up extra support on the outside that you have to remove after the fact. Okay. It allows you to make parts. This is 1.25 inches by 1.25 inches. Yes?
Really stupid question. Can you use plasma spray to create 3D metal objects instead?
They'd like to think so, because the guys have been working on it for 100 years. My sense is it's still fairly expensive, because each layer is even smaller than what we're looking at here with the melted pool. So to some extent, I would say for making solid parts, this is taking over pretty rapidly to build something from scratch. And who knows exactly what else we're going to come up with. But right now you can make semi-prototypes about 1 inch tall, 1/2 inch by 1/2 inch, and they want to charge $400. So you can think like it's very, very expensive. At the same time, I can make something very intricate that will cost several times more through machining. So you save in any form of process development to the extent that you meet the printing requirements. And it's not really scalable, because if I need 100, maybe I get a deal, but it's not going to be 1/3 of the price, of course. So it's a more expensive process, but if you look at this, you make all these little, rounded shape. You can have a cooling system. You can have all sorts of things all integrated into one piece. There's a company we were consulting with. They wanted to make rings, like engagement rings, using this process, because if you want something very, very special, if I can draw it 3D and you like it, good to go, send it to the printer, But they're still working on it, because if you're going to try to do this process here and melt platinum, it's very, very high temperature. You get a lot of distortion, so there are issues. But definitely you can do it by 3D printing the mold and then doing a casting of that. So it is done quite a bit these days. We're going to go quickly through what we've talked about these 12 lectures. And I think I've been trying to bring back some of these key concepts. We talked about nucleation for the reason that you always, if you're going to go from a liquid to a solid, which was our first topic, solidification, you have to wait long enough so you have all the temperature fluctuation creating this little nucleus that's big enough that you're willing to live with all the surface tension that you created around the particle. And that's the critical nuclear size. If you don't have a mold, if you don't have solidification starting from a surface, you have to wait for hundreds of degrees lower than the fusion temperature to start forming your part. And that's something I know a lot of, sometimes like, oh yeah, I'm going to start forming grains everywhere. So no, the grains always form as an interface. It goes from one side to the other, because if you wanted to start forming a grain ahead of the solidification front, you have to be hundreds of degrees cooler than the solidification temperature, and that's very rare. It will happen in polymer, and by the way, The whole topic of polymer, I'm sorry if we didn't address it. I'll either do it in the spring or at least next time I do this class, because essentially broke it down into introduction to processing and then use of material. And the whole story with polymers is the processes are very different, very similar. It's just the microstructure that's different. And it's a lot of the concepts you've learned will also be applicable to polymers, except you're not forming grains, you're forming the spherulites, and you just everything is slightly different. You're not deforming crystals, you're deforming the crystallites or the amorphous zone, depending on what. A lot of the principle, I mean, I'm going to do probably 4 lectures on it, just so it's all integrated and it's kind of a continuation, but we didn't have to do the opportunity to do it here. And with Professor Eager talking to you guys a lot about steel and aluminum, that's why, for example, I decided to address corrosion of steel at the expense of going into non-metallics. The second topic of solidification, all this idea that you're going to form dendrites a lot of times comes from this segregation of the alloys. So when you try to solidify, lots of times you want to make a pure first grain, and you're pushing away all the alloying element, and when you're done, that's where you get a different structure. So we had all these, the pearlite, if you remember, was formed a little bit this way, where you start forming iron-rich zone, and then eventually you get close to, oh, I got material left, so now I'm going to make a two-phase alloy. The whole idea of not following the phase diagram when you solidify is probably very useful to you. And if you remember, the main reason is in the liquid, it's very easy to diffuse. So typically the composition in the liquid is going to be the same. What's more difficult is in the solid. So if I started with a pure alloy, it's going to continue to stay what it was. And over time, I'm going to start forming more of the alloying element. So that's why, especially for steel, we go through deformation processing, because as cast, we get the structure that is different from the edge to the core, and it has all these big grains that are visible. In deformation processing, one key concept that I think I try to convey is if I go to high temperature and the steel is hot and I keep deforming it, I get this dislocation structure on the inside that kind of stays the same. So it's becoming kind of a viscous material that I can keep deforming and keep deforming. If I go faster, lots of times, we didn't talk too much about this, but my resistance is increasing because I don't have as much time to recover all these dislocations that we talked about or to recrystallize. So I'm increasing my resistance. If I go slower, then I'm becoming softer. So there's a lot of optimization going on, but a lot of the basic idea is the metal will take a beating. I mean, you can go through thousands and thousands of % deformation as long as you do it at a rate that your dislocation structure and your grain structure keeps a certain steady state. Now we talked more about what happens to the grains themselves. So, and that's a topic that I get asked about a lot of times. So it's not by deforming itself, we don't really refine the grains. It's when you recrystallize, when you go to this grains that has a lot of dislocation, depending on the condition, when you form these small grains, if I can maximize the number of grains forming at the same time, that's how I get a very fine grain structure through deformation processing. We're not talking about electrodeposition or forming nanostructured material here. This is conventional processing. You can make ultra fine grains through this process that would be less than a micrometer in size, but a lot of times we're talking more like 10 micrometers for steel, and even a little more for aluminum and copper. If you remember our discussion with steel, we talked about quenching it. When you quench, you're preventing the diffusion and you're forming that martensite, and that's how you make it really, really hard. And again, you can temper that martensite, and that's how most people do. A lot of times you want to soften it because otherwise you don't get any ductility whatsoever. The regular structure, if you oven cool or even if you air cool, is the perlite, and that's the first phase that formed from the austenite here. So it's a solid to solid transformation, and then you form that first, and then when you had enough of it, you had zones that had higher carbon content, and that's where you form your perlite. You get the two-phase with the cementite and more ferrite. So the white in this structure is essentially the same white as this one. It just formed later from the austenite. And in this process, you you change the austenite that again is non-magnetic into steel that is ferromagnetic, and if you put enough alloying element, really that's how you get our austenitic stainless steel. You prevent that transformation from taking place, so you keep the high temperature phase all the way to ambient temperature and lower. It's good because steel tends to be brittle at low temperature. We haven't had the time to talk about that too much. The other heat treatment that we emphasize, and I mentioned it, and essentially it's called dispersion hardening or precipitation hardening, is the general idea that I take the microstructure and it's super saturated. Say if it's aluminum, it could be magnesium, it could be copper. I take that at high temperature and I freeze it. So I keep a super saturated solid at ambient temperature, and then I heat it up a little bit, and that's our aging. That's where we start forming these very fine particles, and then you decide when you stop, if you're looking at that hardness evolution, you're going to go through a peak where the dispersion is at this critical size where all of a sudden it's interacting the most with the dislocation, and that's how you get the hardening. So this concept is used with stainless steels. You have a lot, because stainless steels tend to be soft because they are that austenite. That's the high temperature phase. It's very deformable. So you can create different kinds of precipitates in the same way that you do with the aluminum, and that's used for fasteners, for example, quite a bit. Because you do want their strength. And you form them to the geometry exactly you want, then you heat it up. The same way when we were talking about the aluminum fuselage, you make the shape you want and you heat it up, all of a sudden it's becoming super strong, and that's ready for service. The surface treatment is a topic I know I didn't cover everything. I wanted to talk to you about shot peening, for example, which is process where you hammer the surface with beads or small particles, and that deforms them. So if I take the surface here, I'm sure you can understand. It's used a lot for aluminum. It's used for aircrafts, helicopter blades. We used it quite a bit. The idea is, say if I start with a fresh surface, instead of trying to harden it through any surface treatment that we talk about, I just come with beads, and then I'm coming multiple times. So this is essentially, could be a little bit like sandblasting. So I'm shooting beads on the surface of a superstructure for the aircraft. And each time I hit the surface, it's like forming an indent. But if my beads are small enough, what I do is I get a compression layer on the surface by poking it, and then I get tension underneath. Unfortunately, you can't win this battle. So you're increasing the surface resistance, but you do end up with tension underneath. That's free body diagram. You start with no stress. You come and you hit the surface. So by plowing the material, you try to expand it. And when it's unloaded, it's trying to come back. It can't, so it's in compression. But what you did is you did stretch permanently what's underneath of it. It's used, the main reason for doing this is fatigue resistance. If you have cyclic loads, you worry about forming cracks on the surface, so that's a way to minimize, if not eliminate, the crack initiation. It's not 100% reliable because there would be one area where the two beads coincide, or you at the corner, or you in a little radius, and that's why a lot of times it's an added benefit. It's delaying the crack initiation. But when we do this, a lot of times, when in terms of design, we still consider, oh well, it may start cracking, and we're going to pick it up by inspection and replace that component. Yes.
How big are the shots that they're firing?
Millimeters. I've seen the room of it, and you know, they try to and they clean it and they reuse it again. It's a very interesting process. It's automated, but you know, when they're done, you can walk by and they do all sorts of cleanup. The issue is always to control enough the angle that you hit with the bead as well. There are variations of this that's called mass finishing. In mass finishing, you take the parts and you put them in a slurry, and you kind of grind them or sand them in the process. So the slurry is the particle that creates the adhesion, and you say you create enough movement that you're eroding away, or you're abrading away the surface, and you finish it. I've seen it confused with what I call shot peening, because they will use some form of a peening term. Sometimes the chain that I brought to you, the aluminum chain, was apparently shot peened. I would say it's just mass finished to clean it up, essentially. So it's very different from my standpoint. The shot peening I'm talking about really creates that compression layer on the surface. So the other surface treatment, the one we talked about a lot because it was tied into all our heat treatment, was to diffuse nitrogen or carbon into the surface of the steel, and then go through the heat treatment to make a very hard surface layer. And that's very typical of self-drilling fastener, is one example that we went through together. After that, we talked about welding. It hasn't been too long enough. I don't think you've forgotten a whole lot. The general idea with welding is, yeah, you're making a melted metal that is very, very movable, if you will. So we were talking about the melting pool having the impurity going to the surface. It's so hot that the diffusion is really, really fast. And one of the issues is always to control that melted pool. And from what we've learned today with the laser sintering, it's very, very similar, except the laser will really stay at a point for a certain amount of time and then move on. So instead of being continuous like we are in welding, it's really spot by spot. And then you wait long enough so it cools off, and then you do the next one. In welding, you can do the same. You can do multiple passes. The main drawback of welding is the consequences on cyclic loads, because you create a cast structure, you create that heat affected zone, you created all these residual stresses. So here, if we're talking about putting compression on the surface, well, you're putting tension when you're doing welding. So it's a problem for that. So I think you get the idea. In terms of use of materials, this is an example of a specification for making pipes for a very specific application. There's a lot into the processes. It will tell you, make sure your grains are fine, make sure you do your heat treatment correctly, and by the way, inspect for cracks, inspect for this. So there's just a lot beyond just the fundamental concepts. And it's very important for you, if you're going to ask for someone to give you a piece of steel, think about, okay, what kind of standard steel do I want to use? There's ASTM standards for that. If you just say, I want this composition of steel, it's way, way too general. So you can have essentially performance spec, which is more common. It says, I'm going to have these minimum mechanical properties. Or you can have kind of recipe specs. The AISI specification is a good example, where if I say I'm getting a steel that's at 1020, all it says, it's got 0.2% carbon. Okay, is it good or not? You know, is it a fine grained structure? Is it quenched, tempered? There's nothing about it. So That's just good to say when I'm specifying a material, just try to think about what else you want other than what you're actually saying. Be mindful of what you're actually saying. But it's a topic I cover typically in the spring. We're not sure 100% we're going to be doing it this spring. It's being discussed right now. We're still early in the semester, but the idea is to go beyond the fundamental and say, okay, if I'm going to use a certain piece, should I use metal or plastic? What determines how to do that is really what I'm talking about in the other class. This is an example. You see a lot of cracking, small cracking, because of the environment. So we think of plastics as resistant to the environment, resistant to corrosion, but in reality, they have their own issues as well. They're very, very susceptible to oils. So if I use a lubricant to prepare a system, a plumbing system, it can create small cracks in the plastic components very easily. It's like a solvent essentially. It's not resistant to any solvent. That's how we put pieces of pipes together. We just use a solvent, melt them, and put them together again. So what makes a lot of their advantages also makes for inconvenience, for service reliability. These are high pressure, so for a sprinkler system, all that collar pipe is for a sprinkler system. It's meant to go to about 200 psi, and it will do it unless you start having contaminants of all sorts of kinds. And that's what people have learned in the industry over the past 10 years. And now we try to make the resin more resistant to common contaminants, but it's not easy. I appreciate the time. I hope you enjoy the class, and definitely welcome the feedback. I've been trying to go a little slower. I used to try to cover more in less time, but I'm trying to make it. So let me know what you think. I'm really interested. Thank you. Thanks.